Hi, I'm Justin Bro with Argonne National Laboratory. Today we're here at the Millennial Nuclear Caucus, and we're going to be taking a tour of the expo space. So Mike Mueller from the Office of Nuclear Energy is here doing the videography with me. So say hello, Mike. There you go, there you go. So today we have a wonderful expo space for you guys to see all the amazing nuclear energy technologies that are currently in production. And I want you to follow me this way. We're going to take our first talk over here and check out what's new. Now, this is the Next Generation Nuclear Society, and they'll be able to talk to us about what young people basically are doing here at Argonne National Laboratory.
So I make sure that those who need nuclear technology, they get it, and that it's used in such a purpose that is conductive with what they say.
So in front of us we have Andrew Breshears. Am I pronouncing that correct?
That's correct.
All right, I'm Justin Bro.
Justin,
Very nice to meet you. So we're here on Facebook Live, and what we want to find out is who are you and what is a nuclear generation, next generation society?
Okay. So I am with the Nuclear Engineering Division, and what Next Generation Nuclear Society is that it is a way for those of us who are early career to be able to get out into the community through professional development, through education and outreach, and doing societal events as well, such as lunches together. And it allows us to build deeper bonds in our community, with each other, and with those who are later career here at the lab.
Okay. So have you done any particular outreach events recently, and what do those entail?
Okay, thanks. So one of the events that we did was called Engineering Week, and we went to the Illinois Institute of Technology, and we had various items such as the ones that you can see on the table behind me there at the event, and we were showing K through 12 students some of the things that we do as engineers, and especially nuclear engineers, and kind of give them an insight into our world and get them curious about what we do as engineers.
That's what I'm thinking. I can't imagine, when I was a kid, I didn't know what a nuclear engineering did. So so you have the opportunity to impress upon these kids that this is a viable option for them. Is that what you're talking to them about?
Yeah. I mean, probably part of the reason why you never knew what a nuclear engineer was is for the last couple of decades, we've really been closed off, and we haven't done a lot of outreach. I was sort of the same way. And that, as a kid growing up, I didn't know what a nuclear engineer was. It wasn't until my family moved close to a national lab that I knew that this was even around. And it was through the outreach that was done there that I finally got involved. But, I was only one out of a class of 360 people at my high school. How many other people really knew what a nuclear engineer was or what a chemist was? And so, yes, what we're doing is that we're letting people know who we are and what we do and how we contribute to society. And by doing so, hopefully we can get other people interested and curious about what it means to be an engineer or be a mathematician.
And excited.
Yes, okay. Of course, yeah.
So you have some things on your table here. Why don't you take us through what these are and what you'd like for us to know about these things?
Okay, so first here we have what's known as a manipulator. So when we're working in high radiation fields, of course you can't touch stuff with your hands without getting too high of a dose. So this really shows or illustrates to the kids how difficult it is to work with just common materials with a manipulator and trying to do everyday event.
Okay, I'm gonna try this right here. So you guys got me here. I'm gonna try to do the manipulator, and Mike's gonna hold this mic. So this is, I have to try to move these blocks one on top of the other?
Yeah. Try to play Jenga like you normally would.
Oh, wow.
Yeah, exactly.
This is more difficult than it actually looks. Okay.
Yeah.
All right, okay.
No, it's really difficult.
All right, me being able to play Jenga with these blocks does not mean I'm a nuclear engineer, is that correct?
No, but you're certainly on the way to learning the skills.
So I can see how this could be really instructive to people who really have no idea about what it takes to be a nuclear engineer or just one aspect of it.
Yes, that's correct.
Okay, all right. So thank you very much for that. And so I see you guys have a little bit more display over here. So what are we looking at over here?
Here's our set of 3D printed objects. Sorry. Okay. Well, here are a set of 3D printed objects that we use to basically use as props for our outreach. These are basically demonstrations of the sort of 3D printed objects that you can make. Some of them you can see are actually not able to be fabricated by traditional machining, so you end up having to rely on 3D printers to do. It basically opens up, a whole lot of possibilities that otherwise you couldn't do. It takes the challenge of building a ship in the bottle when you can build the ship in the bottle at the same time.
And just so we can tell for our viewing audience, none of this is nuclear because it's 3D printed. Is that correct?
No, none of this is nuclear. It applies to both nuclear and chemical engineering. There are all sorts of applications for it, to electrical engineering, to medicine, prosthetics, dentistry. So it's a very exciting field.
Well, thank you so much. We're going to go on to the next event, next booth. There's a lot of stuff here, so come on, follow me this way.
Sorry.
Pardon me, and I'm knocking people over, but follow me. So there are 6 to 7 presenters here. We're going to go to each table and find out a little bit more about what they're doing. And we can see on the left side here, this is an actual robot. Where people can actually manipulate. So if you see this right here, you can manipulate the robot from a distance instead of having to be at the actual location. And I think that we have the gentleman right here who is... Hello, what's your name?
Hi, my name is Young Park. I'm a principal mechanical engineering at Argonne National Lab. Okay. Yeah, I'm supervising the robotics program in our nuclear engineering division.
Okay, so tell me, because I was a philosophy major, we're important. I'm serious. So, why does Argonne need robots? Like, why does nuclear engineering need robots?
Oh, yeah. The robot was first invented in late 1980s. Because we needed, Argonne was required to handle radioactive materials. So we couldn't have the human operators to go there, handle it. So to save the human from the dangers, we introduced robotic manipulators to do those tasks. So from early on, we needed robots to do hot cell operations to very fixed environment. And later on, we need more application of robots in more sophisticated and more challenging environment, like a nuclear reactor maintenance, nuclear waste handling. Those require tasks in more unstructured environment, handling more heavy objects, and more dexterous contact manipulation. So we are carrying on those old teleoperation, meaning controlling robot from a distance manually using our operator interface. From those old technologies, now we are trying to develop more enhanced technology to meet those more challenging tasks.
Now, you mentioned that it was in the 1980s when you first got the first robot, but this is actually older technology, right? So this started Argonne in the 50s or 60s, if I get it right?
Oh, it was actually 1950s. It was first developed. So there was a master-slave manipulator and a force-reflexive manipulator. Now, to do these new tasks, more challenging maintenance and waste management tasks, those technologies were either too difficult to use or too complex to use. So what we try to do here is use a new technology of augmented reality to provide a better operator interface to make the teleoperation simpler, more precise, and more effective. And also at the same time, we can deploy simple and rugged robot to the remote sites so that we don't have to deploy very complex robot that cannot be really deployed and have a travel down there. Right.
I see a gentleman, he's manipulating right now, and Mike's already on the case. So if you want to explain what this gentleman is doing.
Yes. So what he's doing is he's using this hand controller, and that hand controller allows him to touch certain geometry in augmented reality environment. You see those are gray circles and planes, and those are actually not only visual visual but actually touchable environment, touchable objects. So you can use that to feel and see and use it to operate the robot more precisely and easily.
So is there feedback? So if he touches an actual physical object, he would be able to feel that feedback in the device he's using to manipulate it?
He can feel the surface, like using a straight edge to draw a line.
Yep.
You feel and use the straight edge, the physical interference to help draw the straight line more precisely and easily. It's the same concept. You can feel and use that surface with that haptic device, and by making the robot follow the surface, you can do the teleoperation easier, precise, and more efficient.
So precise and more efficient. So thank you so much for your time.
Thank you.
We're going to move on to our next stop on our tour of the expo here at the Millennium Nuclear Caucus. Yes, and there is food for the hungry millennials that are meeting with all their, hopefully, future opportunities. So let's keep on moving down here.
And traditionally these are made with, traditionally they're made with just using the solar contribution, but in order to supercharge essentially that process, we use the excess decay heat.
So here we're talking and we're listening to Aries Loomis. He's with CEO of Loomis Industries. And the background is the proposed technology that Loomis is attempting to develop uses safe, renewable, and passive systems that not only safely stores and cools the waste, but also generates electricity. The technology works on the principle of hot air rises. Accordingly, this design incorporates wind turbines along the tower to generate electricity from heat rising from the dry casks. So we can get a little bit closer, and maybe we can get Aries to talk to us. We can find out exactly what he's talking about.
Traditional wind turbines that you see, you go up to like 25 meters per second without wanting to break, but these are a little bit smaller and robust in how much wind they can take. Hi.
How you doing?
Hi.
Justin Bro with Argonne National Laboratory.
Hi.
So we're on Facebook Live, not to put you on the spot.
Yeah.
So say hello to all our Facebook Live watchers.
Hello.
We are going around the expo, finding out what the different presenters are talking about and presenting. So why don't you tell us a little bit about your invention?
Okay, hi. Do you want me to take this? Or yeah, okay, all right. So we're Lumos, and we're working on a way to make nuclear energy more sustainable, essentially. What we do is we take the excess decay heat that comes off of dry casts and other waste forms in order to generate electricity. So yeah, through a kind of a hybrid nuclear renewable system. Yeah.
How did you come up with this idea? Because this sounds really novel.
How did I? I did a study abroad program with the Swedish Nuclear Waste Management Company, and I saw how, traditionally in nuclear we cool waste in one of two ways: in dry casts or in pools. And we waste a lot of energy and money to cool off this waste. And I just thought, while I was there, why don't we try to generate electricity off of this? So that's kind of where the idea came from. And this is kind of an older technology. It's called a solar updraft tower. And essentially what this does is that, so cold air is able to come in from the sides, and what comes up is solar radiation. Okay, so under this clear plastic region that you see right here, solar heat comes in and heats up the air. And what does hot air want to do? It wants to rise, right? So all of that gets funneled into the center where it moves turbines and generates electricity.
That's amazing. That's amazing. Thank you so much for being here.
Yeah, thank you so much.
Appreciate it. All right.
Robert Eshelman just checked in, said hi.
Hey, Robert. Thank you. Thank you for saying hi. We're going to move on. All right. So where should we go next? Let's come over here. I see some really cool 3D printing conversation going on. This is advanced manufacturing for nuclear development, nuclear fuel development. Let's see. Maybe we can see while he's talking some of the things that they actually make insofar as 3D printing. That person is not 3D printed. You can tell because he's moving.
Zane Abbas says hi.
Zane, how are you doing? Thank you for saying hi.
Zircon is kind of like a surrogate.
So if you can look, these are 3D printed materials used for nuclear applications. And that's a project going on here at Argonne National Laboratory.
Zane says he loves Argonne Lab.
Oh, thank you, Zane. We love you too. So let's see if we can come over here and talk to Shumit. Shumit, Justin, how are you doing?
Doing well. How are you?
All right. So why don't you give people out in the Facebook audience your name and what you do here at Argonne?
Hello, I am Sumit Bhattacharya, and I am a postdoctoral student in nuclear engineering department. And I am, as you can see, I am working on additive manufacturing of nuclear fuel development. And we are
So additive manufacturing, is there another word that goes by?
so additive manufacturing is another word for 3D printing.
So you're 3D printing cool things, is that what you're saying?
Yeah, basically so. Yes. And so what we are showing here is that we can use 3D printing to remove the archaic process of hot rolling, hot isostatic pressing, which is very expensive and very wasteful. So with 3D printing, we can not only reduce the waste, but we can get those intricate, difficult shapes, which is achieved by thousands of steps of machining in one step with 3D printing.
So we're talking about reducing waste, number one, but also those difficult things that you basically can't make through a conventional manufacturing process, you can do through a 3D printer, additive manufacturing.
Manufacturing, that's definitely.
And so what are you doing here at Argonne? Do you want to show us some examples of what you've been working on?
Here we have two different things, two different processes that we have gone through. One is the metal powder impregnated plastic filament, which you are using to print the pellets of uranium dioxide, and for stereolithography, which you are using generally for printing both ceramic and metals. And here we have few examples that I want to show you. So this is actually a surrogate for uranium molyfoil, which is actually here it is copper. Unfortunately, I cannot bring uranium here. So copper having the same density as well as the ductility and the melting point like uranium moly. So, and you can see we have printed it in one step, which takes 9 different steps to produce this foil.
So 1 versus 9 steps. Amazing.
And so that is what we have here. And another thing that I want to show the amazing thing, because generally with simple machining processes, creating a curved surface like this is very difficult in one step. But you can print this structure at one go. So you can see the curvature, how it goes. So you can print this in one step. So another thing that we have. And on top of that, we can also print not only metals, we can print ceramic as well as metal pellets. So this is a pellet which is actually a replica of a UO2 pellet, which is uranium dioxide, which is a nuclear fuel.
Still for the camera?
Yep. And so this pellet is exact replica which goes inside a reactor. And so we have shown the demonstration that with 3D printing is not only limited to plastic, we can do ceramic, we can do metal, and that's the breakthrough that we have done in Argonne.
So why are you coming to Argonne to do this particular study?
In Argonne, generally all around, Argonne has been the place for development of nuclear technology. And Argonne has developed a lot of nuclear fuels. So Argonne has those old technologies of rolling, of sintering, of pellets, all these things. And every day I can see how wasteful and how inefficient those processes are. And with 3D printing, we can, so that's gave me the idea that why not use 3D printing. And with 3D printing, we can reduce those, as I said, wastefulness and have the structure directly in one step. So,
thank you so much. This is amazing. Thank you. Yeah. All right, so we're going to come over here, and it looks like we have another Argonne nuclear engineer, Ian Foster, who's actually also part of Chain Reaction Innovations. That is a tech, for lack of a better word, a technology incubator for small businesses that want to make it to the next step with their technologies. And we have Ian Foster over here. So, hello, Ian.
Hi.
How are you?
Good, how are you?
All right, do you want to introduce yourself for our Facebook Live audience?
Yeah, sure. Hi, my name is Ian Hamilton. I'm CEO and co-founder of Atlas Energy Systems, my startup company.
So describe to us what Atlas Energy System is and does.
So we are primarily an energy technology company, actually developing technology for use in nuclear power supplies and nuclear reactors.
All right, unpack that. Nuclear power supply. That sounds difficult?
So it is. It actually very, very much is. So portable nuclear power supplies are radioisotope batteries, actually. So the best example of it is on the Curiosity rover on Mars. So there's a big 138-watt radioisotope battery there. NASA paid $126 million for it, something around there. We're trying to develop different technology to make it more efficient and hopefully cheaper. So that's the main goal there.
Less than $126 million.
Yeah, hopefully.
Okay.
Yeah, hopefully.
So I understand that you're also part of Chain Reaction Innovations here at Argonne. You want to explain a little bit what that is and why you're part of that program?
Yeah, of course. Yeah, the Chain Reaction Innovations program is actually a government accelerator, incubator type thing. It's funded by the EERE's Advanced Manufacturing Office within the DOE, and it started out at Cyclotron Road at Lawrence Berkeley Lab. Now it's here and Oak Ridge National Lab. It's actually a 2-year fellowship where we get funding, salary, and health insurance, which is great as a startup company, for 2 years, and as well research funds to develop and research our technology here at the National Lab. And so the key differentiator from other startups and incubators like Y Combinator, stuff like that, is that these things can't be done like in your garage. So I'm actually here using a 3 million electron volts electron beam to simulate ionizing radiation. First year of grad school, I looked into either making one or buying one. Very quickly became apparent that they're around $6 to $10 million. So even though I've got money here to research and whatnot, this having access to that facility was worth more than the research funds. So it's a very interesting and cool program.
It seems like even more too, because you don't have because you work here with your PI, but you're not just talking with your PI, but Argonne has a whole ecosystem that you can derive information from.
Yeah, very much so. Yeah, we're talking to all kinds of people. Actually, Latif Yakut, who I think you guys his research group just talked to, they're interested in actually 3D printing some nuclear materials and stuff like that. And so some of our things would love to be 3D printed, and so even though he's not even directly related to my original research project, we started talking with him and getting some of his advice and expertise and things like that. So it's a great ecosystem, especially for nuclear engineering.
So do you have an example to show us of what?
What?
Do you have an example of your nuclear battery?
Yeah, I mean, this would be a larger one. So this was just a mock-up design. This is actually the same size as the military BA5590 battery, which is...
You know, all those numbers are... Yeah, you got to memorize those.
It's important because on a typical 72-hour mission, a soldier carries 6 of these at 3 pounds apiece, and each one only lasts a couple hours. So actually, the military is interested in compact nuclear power supplies that last years instead of an hour at a time.
That'd be better than 3 hours.
Yeah, so that'd be better at 3 hours. Obviously, there are some concerns with carrying around nuclear material and stuff like that. So we're looking at more like stationary applications, deep sea, underwater unmanned vehicles, remote charging stations for maybe drones, or actually the Alaska Center for Energy and Power is actually pretty interested in some of these things for charging some of their remote communication networks that are out in the middle of nowhere. So,
well, thank you so much for talking to us.
Yeah, very much.
It's amazing work.
Thanks.
Thank you.
Talk to you later.
Lester joined. He's watching now.
Paul, hey, how you doing? You got to say hi, Paul. Thanks for joining us, Paul. We're going to move on to our next display here. So we're looking at nuclear batteries. We saw 3D printing for nuclear applications. We saw robotic arms. What isn't there in the nuclear energy space that can't be done? Let's move on next. So here we're looking at a test reactor, a JM1 reactor. And the gentleman who's going to explain to us in a couple of seconds is going to explain to us exactly what this is. But I believe, Mike, if you want to just check out this one more time, this whole thing is 3D printed. So this could very well be, and he's going to correct me when we see it, but this could be a 3D printed test reactor. But we just want to make sure that that's correct before we go there. Hey, how you doing? And so, what's your name?
Francesc Puig.
And what do you do here at Argonne?
Okay, I'm a nuclear engineer. I work at the research reactor and test and research reactor department. Sorry, and I'm mostly involved in the research and test reactor conversion, which is what we call the process we call for replacing the highly enriched uranium fuel with low enriched uranium in these research reactors around the world, so they become proliferation resistant. And so it's not a safe security concern anymore that somebody would remove the fuel from these reactors. It could not be used for, I don't know, let's say.
So you're essentially converting nuclear reactors.
Yes.
Okay. And what is the purpose of that again? For safety and security.
Yes. So potentially highly enriched uranium could be a safety concern or security concern. I mean, some, let's say, terrorist group or whoever could make wrong use of that, nuclear device and so on. So if you avoid that kind of fuel being available anywhere, basically, so you would remove that kind of risk or potential threat.
And this isn't a new program. This has been around for a while, right?
For about 25 years already.
And do you have idea about how many nuclear reactors have actually been converted?
Yeah, over 70.
Over 70%. 70 facilities. Out of how many?
So it depends, because some of them were not originally filled with highly enriched uranium. So there are some that don't need to be converted. And right now there are about 70 more that are kind of pending or are planned to be converted in the next years.
So Mike, our cameraman, has the perfect idea, is looking at this test reactor, and as I understand, this is 3D printed, is that correct?
Yes.
So this is an actual reactor that's 3D printed?
Yes. This is a real scale 3D printed model of a reactor in Jamaica.
Do you want to explain to us what this reactor actually does?
Well, this reactor, as I said, is a research reactor, so it's meant not for power production, but for neutron irradiation. So it's a technique they call neutron activation analysis. So you put samples of a material inside the reactor, you irradiate them with neutrons, then they become activated and they become radioactive temporarily. So then you put the material into a detector and you measure the spectrum of radiation they emit, and you can infer the composition of the sample.
And so you said this is what they use in Jamaica. This is one of the. So
we have a question from the audience. Victor wants to know what kind of fuel is used in the reactor.
What kind of fuels is used in the reactor? That's a great. Thank you, Hector.
So since 2015, it's low enriched uranium fuel, and actually initially was uranium aluminum alloy, but we converted to what is more similar to actual power reactors. So it's uranium dioxide. So it's ceramic uranium dioxide pellets inside zirconium alloy metal tubes or cladding.
That's amazing. So if you're going to use this test reactor in Jamaica, what are they testing for?
What do you mean?
What are they testing for? So they're going to put a sample in there. Yes. So what are they testing for?
Many different applications. One of the important ones, just highlight, it's important to highlight perhaps, is that they had quite a lot of activity in terms of bauxite mining in Jamaica. Okay. So you may have a lot of heavy metals associated with that kind of activity. And since probably they did not do the mining in the safest way possible and so on at the time, so there are contaminated water sources or soil that has been contaminated with heavy metals. So it was a significant concern to try to identify which water sources or springs and so on were safe for human use, what soils, what crops could be planted and so on in what areas, so they would be safe for human consumption. That is one of the many examples, but this is one of the main efforts. They basically mapped the whole island for cadmium, mercury, lead, arsenic.
So that's really interesting to me, because I had never thought that you can use a nuclear test reactor to look for contaminated water.
Right.
for that particular purpose. And a lot of people that don't either not in the nuclear engineering space or this is just not something that you follow. This is very real relevant research that's going around the world where people in Jamaica are using this test reactor. This is the actual size, right?
Yes.
This is the actual size of the reactor to test for contaminated water around the island so they can avoid or they can have proper cleanup done. That's amazing.
Yeah, they also did some research about how these heavy metals were kind of uptaken by the crops. So you have some soil that it has some contamination of heavy metals. Maybe some crops may not actually get that heavy metals into the plants itself or into the fruits or whatever product you get from that. So even if the soil is contaminated, you may have some options which would be safe for farming, maybe not some others. So it's a lot of also research in that way. So you could have kind of important economic activity and still, do that in a safe way. So there's no concern in terms of the food being,
Absolutely.
health concern.
It's all about safety.
One more question.
Hector has a question.
So, the type of coolant that you use, is it water?
It's light water, so it's passive cooling, so just natural circulation. So you don't have any pumps, anything. So it's inherently safe as well.
Excellent. Hector, thank you for that question. We're going to move on. Thank you so much for your time. Appreciate it. There are tons of things, and what haven't we seen, actually? I think we've seen everything. Or maybe we can talk to Nuclear Matters. Let's find out who Nuclear Matters is. Yep. Hello, ladies.
Hi.
Hello. You want to say hello to our Facebook Live? So we're finding out this is Nuclear Matters,
Yes.
and I just want to let you know that we've refollowed you on Twitter.
Excellent.
So we're following. So explain to us what Nuclear Matter is.
So Nuclear Matters is a grassroots organization that is promoting and advocating for the benefits of nuclear energy. So our core mission is to educate and mobilize new supporters for nuclear energy and trying to get them to talk to their communities, their family, their friends about the benefits of nuclear.
Is that something that's not already happening?
It's not happening enough. It's not happening enough. So we're trying to, provide people with the information that they need, get them connected with their lawmakers as well, and really try to, mobilize support for the industry.
That sounds amazing. Are you in any particular areas of the country?
We are all across all 50 states. So our entire community is about 500,000 people, and we represent all 50 states of the United States, and we concentrate kind of in the states that need us most, but we're all over the place.
Well, thank you so much. That's Nuclear Matters Grassroots. Thank you. And I think that's it for us. So we're gonna cut it right there. This has been amazing. We saw 5 to 6 different amazing technologies by people who are changing the face of nuclear energy, and that's real. That's here at Argonne National Laboratory, and that's here at a lot of sites throughout the country. But I just want to say thank you so much for joining us. This is Argonne National Laboratory. We're at the Millennial Nuclear Caucus at Argonne National Laboratory. Thank you for Mike Muller for being our camera guy for today. And I want to say thank you and have a great day.